Now let's move to the inlet velocity limitations. In this case, we have to look also to the vac of Mach number at the eye of the centrifugal compressor. This is where the inlet part and the air flowing into the compressor. Let's assume that we need to avoid the high stress due to the shock waves, and it again shock waves came from the high velocity when it reached a high Mach number. Therefore, to keep it stable, the blade speed is to keep below 450 meter per second. So there will be two extreme working conditions or operational conditions. And we see on the left side here, this is where the tip diameter, the eye tip diameter is large and the absolute or the axial velocity C1 is low and the blade speed U is high. Then we have this type of velocity diagram. This is when the geometry or the eye tip diameter is large. On the opposite side, when the eye tip diameter is small, we have the opposite conditions where C1 or the axial or absolute velocity is large and the blade speeds of U1 is small. However, these two conditions share one common velocity component, that is W1 here, or we know it as the relative velocity, and it will play the role when we assess the vac of Mach number at the inlet part of centrifugal compressors. Now let's begin that we know the continuity equations, that mass flow rate is a function of density, area, and the absolute velocity at the inlet. Just like the centrifugal pump, centrifugal compressor characteristics can also be seen from a characteristic curve that normally consists of a plot of pressure ratio and flow parameter that is a function of mass flow rate, temperature, and pressure. This fairy graph here is the theoretical characteristic curve of a centrifugal compressor. Now let's see at point 1. Now let's assume that the centrifugal compressors in this case is equipped with a flow control valve after the diffuser, and this valve is closed, and the pressure ratio from the inlet across the diffuser outlet will be developed. So then we have the high pressure ratio here due to the valve is being closed. And now we begin to open the valve, and the airflow begins, and it leaves the diffuser, and it contributes to the pressure ratio, and then it develops the pressure ratio until it reaches its optimum or maximum value at point 2. And then by increasing the mass flow rate as the curve moves to the right side, we see a slight decrease in the pressure ratio at point 3 when we increase the mass flow rate. But the difference between point 2 and point 3 is at point 3 we reach the maximum efficiency of a centrifugal compressors. And then if we further increase the mass flow rate to point 4, we see this is the point where the pressure rise is 0. Theoretically, at this point, it can be reached when all the input power is absorbed to overcome internal frictions between gas, air, with the internal part of the compressor. As this is just a theoretical curve, this point 4 in actual conditions will never be reached due to some reasons. First reason is due to surging, and the second one is stall. Surging itself normally occurs inside the diffuser passage, where frictional effects of the fluids next to the fan surface retard the flow or disturbing the flow. We can avoid or reduce the effect of surging by making the number of diffuser fans in an odd number. This might lead us into avoiding the surging phenomenon. On the other hand, stall itself is a separate phenomenon that might lead into surging to happen, but it can occur on its own before surging occurs. A stall normally can be observed through an audio observations, and since the compressor will create a scratch sound during the operations. And the other part to characterize the compressor or centrifugal compressor characteristic is that we call as chucking. Chucking itself might occur at the inlet, or it might also occur at the impeller or at the diffuser itself. So from these 3 parameters or 3 phenomenons, surging, stall, and chuckings, is to inform us that there are certain limits where the mass flow rates in a compressors beyond which the flow becomes unstable. So let's say at this theoretical graph, so 0.5 is the optimum value where we can put the mass flow rate into the compressor, since there are no more pressure rise if we keep pushing the mass flow rate into a higher value.